So we said in this video we are going to discuss the principal component analysis, PCA. Just like in our ridge regression video, I'm going to put a lot of theory in this video so that we cover a lot of ground. And if you do not understand, I'm going to in the next video we're going to do a very simple example just to cement some of the theory that we're going to discuss in this video. Same thing that we did for ridge regression. Hopefully that helped, because I know the first video was a bit of theory, and then the second video tried to use a simple example just to explain the principle. So that's what we're going to do here. So principal component analysis, it is used in both dimension reduction and unsupervised learning, but for our purposes right now we're going to use it for its power in dimension reduction, right? So imagine we have ad spending by Coca-Cola, ad spend by Coca-Cola in thousands of rands. So rands is just a currency. It's a currency in South Africa where I am. So it's going to be ad spending in rands, and this is going to be population per country in Africa. So this is going to be in millions. This is going to be in millions of people, not rands, Easton. This is going to be millions of people, right? In millions of people. So of course we are going to have different ad spending depending on how many people there are. Countries like Nigeria that have many people, maybe Coca-Cola would want to put a bit of money in there. Countries like Lesotho that doesn't have many people, probably they wouldn't want to put much ad spending there. Cool. So I'm going to define something called the principal component direction. Principal component direction. This is defined as the direction the data along which observations vary the most, right? They vary the most in that direction. So that is called the principal component direction. The direction in which the observations vary the most. Observations vary the most. When you just look at this graph, you can already tell which direction the observations vary the most. And I'm going to draw it now. This is the direction. I think you can already see that this is the direction that the observations vary the most. They vary the most in this direction. There is no other direction that they vary the most, because if you draw a line like this, a straight line like this, not really. Is it going to be perpendicular to the trend here in the data? Not really. They're not going to vary the most in this. This is the direction they vary the most, right? They vary the most in this direction, and so we called that the principal component direction, right? And this line is going to be exact, we are going to call it the first principal component direction. This is the first principal component direction. Don't worry if you don't. We are going to describe with using an example how we can come up with the component directions. For now, just know the theory behind it, and then we'll describe it. We'll describe an example later, right? So we can see that this is the direction where there is greatest variability in the data. So if we projected, we're going to see this in the next video as well. If we projected the observations onto this line, right? We project all observations onto this line, onto this line, each point. When we project it onto this line, right? We can see that this point is going to be here, and this point is going to be there. It's going to be there, right? This line is the one that gives us most variability, because look at a line like this. If we were saying, but what about the horizontal line? If we drawn a horizontal line like this, if we drawn a horizontal line like that, right? How was when we projected our points were going to be projected like this. Do you know what a projection? Maybe I'm skipping something here. Projection. So when you're projecting a point to a line, you're basically just creating a perpendicular line connecting that point and the line you're projecting to. So let's say this is the line and this is the point. You're basically just creating a line that is at right angles with the line you're projecting to and the point. So that's what I'm doing here. For this one that is slanted, the blue line, these projections are making 90 degrees with that blue line, as you can see. And if you have a horizontal line like this, instead of projecting it at an angle, projection, say from your line, draw 90 degrees going to the point. So that's what I'm doing here. 90 degrees going to my point. Going to my point. So this one here, this point, it has a projection like this to the black line and a projection like this to the blue line, right? To the blue line. So if we project our points, what we are going to see is the variability on the black line is going to be from here to here, from here to there. That is the variability, right? And if you calculate the variability here, it's going to be of the black line is going to be less than the variability of from here to all the points that are between these two. The variability on the blue line is more than the variability on the black line that is a bit slant, that is a bit horizontal, more horizontal. So the blue line is the direction that gives us the highest variability, the largest variability, and that becomes our first principal component direction. That is the direction that we choose, the one with the largest variability. With the largest variability, right? We're going to see an example with calculation. We're going to see how that works, right? So cool. If, for example, let's just say, so that is the blue line. So let's just say the blue line can be rewritten as something like this. We're going to rewrite the blue line as Z1 is equal to 0.83. If you remember, we're looking for our phi's, right? We're going to see how these 0.83s are going to be attained. Pop minus pop. I'm going to explain something here. 0.544 add minus add these are the mean. This is the mean of the population, and this is the mean for the ad spend. And when we subtract the population minus its mean, so each population is going to be subtracted by its mean. Here we are doing what is called mean normalization. I think we saw this before, where we normalize the data using the mean. We are basically just normalizing. Why are we doing that? Because if you look at our data, the population is measured in millions and the ad spend is measured in thousands. Those different scales can be very difficult for our machine learning models. They can be very difficult. We do not want to deal with scales and stuff like that. So here we're basically just mean normalizing. That's all we are doing, right? Mean normalizing. You can write that variable maybe as pop like this, whatever you want to write, as long as you know that first you normalize. After you mean normalize, then your quest is now to calculate. You remember our phi's. This is phi 1, this is phi 2, and this is 2 1, and this is 1 1, because we're dealing with Z1. So imagine we've calculated and then we came up with this Z. We came up with that Z as our Z1, right? These ones here, these phi's, they are called the loading scores. They are called the loading scores. This video is full of theory, but we'll see the practical side of it in the next video. These are called loading scores, right? So we basically found this Z1 or this principal direction by maximizing var 1 of pop minus its mean plus phi 2 1 of add minus add bar. Yeah, so we basically maximized the variance. You understand? We've just maximized the variance. That's what we basically did, right? And for us not to affect the trend in the data by introducing these phi's, we can constrain the phi's themselves. We can constrain the phi's themselves such that squared plus is equal to 1. So once we are like, no, we don't want the phi's to affect, because we will be like, okay, dude, I'm going to put 1 equal to 1 million. And then that's going to affect the variance that was originally in the data. When we limit it like this, we limit it to a range where we know very well that we didn't affect the variance that was in the data. The direction that was chosen was because it was the one that had the one that had the maximum variance in the original data itself. We didn't affect it by introducing these phi's. We did not. That's basically why we have to restrict it to that, right? So so if we are going to create many of these z's, we can do the same thing. We can create many of these z's. We can create a z2, z3, z4, z5, right? In the next video, so here we said it is the maximum variable, right? Maximum. We said our first principal direction, first principal component direction is the one with the maximum variability, right? Or we can just say it is the line closest to the data. It is the line that is closest to the data. This is very important because in PCI we then ask the next question: what does closest to the data mean? We're going to see that in the next video. How do we measure closeness to the data? All right, we'll see that in the next video. Let's see. So that is our first principal component. How do we then find the second principal component? Well, what we can do is, now that we have found our first principal component like that, what we are going to do, our blue line is the first principal component, right? What we can do is then rotate that blue line. We're going to rotate that blue line such that it is horizontal. We're going to make it horizontal, and our points are going to rotate with it. They're obviously going to rotate with it, right? They're going to rotate with it. They will rotate with it. So that now we're going to make it the x-axis, sort of. It becomes sort of like the x-axis. I'm just putting quotes. You cannot see them, yeah, for obvious reasons, but I'm putting in quotes that this becomes our x-axis. We've just made it horizontal. So now what we can do to find the z2, we do not have to do calculations. To find the second principal component, what we are going to just do is to find a line that is perpendicular to this z1. Find a line, sorry, it's not scrolling. Find a line that is perpendicular to this, and this becomes our z2. Find a line that is perpendicular to our z1, then that becomes our second principal component. So the second principal component, z2, it is a linear combination of the variables that is uncorrelated with z1. We do not want it to be correlated to z1, right? Otherwise, if they are correlated, if z1 and z2 are correlated, then there's no linear combination there. You know what I mean? We are pretty much hiding z1 inside z2 if they are correlated. But if they are not correlated, then it means z2 has introduced new information that z1 didn't have at all. And them being uncorrelated, because we want them to be uncorrelated, the consequence of wanting them to be uncorrelated leads to them being at right angles to each other. They do not affect each other at all. The information that is in Z1 is at 90 degrees to the information that is in Z2. You get what I mean? Which means that information does not affect each other. They're uncorrelated. So the consequence of us wanting the principal component directions to be uncorrelated is we end up we are forced to just put them at 90 degrees to each other, which is good for us because once we calculate Z1, it will be easy for us to calculate Z2 because we just look for a line that is perpendicular to that, right? So in our case, because we had that Z1, you remember that Z1 that we had here, this Z1 that we had, our Z2 can be written as something like this. Maybe our Z2 now, our Z2 will come up to be something like this: 0.554 pop minus pop minus 0.839. This line is perpendicular to the original Z1 that we had, right? It's perpendicular to this Z1 that we had. So here we've just described the high levels of what it means to be a principal component direction and what it means to get another principal component direction, let's say from Z1. Because of this, because they are supposed to be uncorrelated, they have to be at 90. They are going to be at 90 degrees to each other, right? This might be difficult to be like, yo, that's too much to take in. Let's go into the next video and look at an example. And the example is going to be so, I hope it's going to be so simple that these concepts will start making sense. Hopefully, after the next video, if you come back to this one, the concepts will start clicking. Will be like, oh, that's why we said this. That's why we said it this. That's why we normalize. That's why we normalized. Or what did we mean by closest to the data? Maybe that will make sense. Maximum variability. What is the effect of that? We'll see that in the next video.